In this one, we start off the same way. We want to find those domain restrictions, so I come off to the side and say, okay, x minus 3 cannot equal 0. I set that denominator equals 0, and then I solve, so I add the 3 to each side, and I find out that x cannot equal a positive 3, so that's my domain restriction. So there's only one this time, and that's okay. Now I want to simplify everything completely, so I'm going to factor that numerator. I build a bridge. Two numbers that multiply to a negative 12 but add to a negative 4 are going to be a negative 6 and a positive 2, so it's an x minus 6 and an x plus 2, all over the x minus 3. And then from here I simplify anything that I can. Well, I can't really simplify anything here. It doesn't reduce. And so really the original problem is fine for plugging things into, or I can even plug it into this version, this factored version of this thing, and think of it this way. Y equals, that's going to be an x minus 6 times an x plus 2 all over x minus 3. Okay, I can plug it into either one of these in this situation. All right. So now I look at my domain restriction. I only have one, and this domain restriction is either a vertical asymptote or a hole in the graph. So I look, did it get canceled out, or is it still there? And if it gets canceled out, it's a hole in the graph. If it doesn't get canceled out, it's a vertical asymptote. Since this one does not get canceled out, it's a vertical asymptote. Okay. So x equals 3 is my vertical asymptote. In terms of my hole in the graph, well, I don't have any other domain restrictions, so there can't be a hole in the graph. The only domain restriction I had was a vertical asymptote, so there is none for this one. Horizontal versus oblique, I look at the degrees. Again, the degree of the numerator here is 2. The degree of the denominator this time is 1. I can't see it, but I know it's there. Since the numerator is larger, I have to do an oblique asymptote this time, and I have to find that through synthetic division. All right, so I'm going to use some synthetic division to find this. So I'm going to take that off to the side over here. I take the opposite of this guy and I put it in my box. So I put the 3 in my box and I write down my coefficients, the 1, the negative 4, and the negative 12. I'm setting up an addition problem. I bring down the first value. I multiply what's in the box times what's underneath. That gives me a positive 3, and now I add straight down. What's in the box times what's underneath gives me a negative 3, and I add straight down. And now the way we interpret this is like a 1x minus 1 with a remainder of negative 15. Well, I just hack off the remainder and say I'm only going to use this first piece, which is y equals 1x minus 1. That's my oblique asymptote. Y equals x minus 1 is basically what I get from synthetic division, except I ignore the remainder. And that's it. Okay? In terms of x and y-intercept, I find these the same way I always have. The y-intercept, I plug a 0 in for x, and I can plug it into the original, or I can plug it in over here. Either way, when I plug that 0 in for x, I should get a a positive 4 out for y, so I get 0, positive 4. The x-intercept, I plug a 0 in for y. I'm going to do that over here in the simplified version, just because that tends to work out a little bit better over here. If I plug a 0 in for y, again, the trick here is I can just set the numerator equal to 0. If you want to cross multiply, you can. When you cross multiply, you'll just have that numerator equal 0. Well, if I have an x minus 6 equal to 0, that's going to give me a positive 6. That's one of my intercepts. If I have the x plus 2 equal to 0, I'm going to subtract the 2 and get a negative 2. That's my other x-intercept. So I get 2 x-intercepts this time, which is fine. All right? And now I'm just going to start graphing these things. Again, I start with the asymptotes. Always start with the asymptotes. So I've got the positive 3 for my, use my green for that one. Positive 3, it's a vertical line. Y equals x minus 1 has a y-intercept of 1 and a slope of 1. So it's a diagonal line. That's what an oblique asymptote is. And then from here, I start plotting the points that I have. I've got the hole in the graph. So let's see, I can plot that hole in the graph. Let me extend my graph a little bit. I cut this off a little bit. So the hole in the graph, oh, there is none. So y-intercept, I move on to that. I've got a positive 4 for my y-intercept, which is right here. X-intercept's at positive 6, which is right here, and a negative 2, which is back here. And really, that's enough information to graph this thing. I know that I have to hug these lines. I know that I'm going to be hugging this line and going through this point, or those 2 points. Over here, I know I'm going to be hugging this line and going through these points, and that's it. Okay, I get closer to those lines, I go through the points, and eventually I'm going to be right next to those lines, and it's describing the end behavior. That's what an asymptote does. Okay?